Hello guys, welcome back to my channel Code Shiba, and this is day 3 of my series where I'll be posting content related to DSA. And today I thought of why not DP. This will be the first lecture regarding DP, and I'll be teaching DP with the help of this problem, climbing stairs, and it is a lead code problem number 70. Okay, so let's start with this lecture. So the problem here given to us is you're climbing a staircase. It takes n steps to reach the top. Each time you can either climb one or two steps. In how many distinct ways can you climb the top? So the thing is that this problem states that we will be given with a number n, let's say, and n, the constraint is n is greater than equal to 1 and smaller than equal to 45. Okay, so n belongs to somewhere like 1 to 45, right? So within this number n will belong, and the problem states that n are the number of stairs. You can have one stair, we can have two stairs, we can have three stairs, we can have four stairs, and we are required to find out the how many distant ways can we climb to the top. Like how many different ways can we there to climb up to the top. Like for example, if we have two stairs, we can go one, two. We either have two options. We have two options. First one being we can take one step, and the second one being we can take two steps. So either we can take one and reach to the second stair, or we can directly go to the second stair. Let's take another pen. We can directly go to the second step by like taking two steps at a time. So we have the number of distant steps we can have right now at this point is 2. Yes, 2. So if we have 2, and if we go ahead if we go ahead and take 3 steps, if you go ahead and take 3 steps, tell me how many number of steps, like distant ways, can I reach. Like 1, 2 and 3, this will continue on here, and 2. So let me just erase this point. So first step we can have is taking one step at a time, this one, and the second step we can do is 2 comma 1. Okay, so 2 comma 1, right? 1 comma 1 comma 1. The first step which we can take is 1 comma 1 comma 1. Second step we can take is 2 comma 1. Third step we can take is 1 comma 2. And like, are there only 3 ways? Yes, there are only 3 ways. As there it is there in input 3. So if we certainly increase the number of steps, we can find more such ways. If we have, let's say, so the thing about this problem is when I was earlier solving it, the the main thing that I noticed is that we can solve this problem if we know the pattern. If we know the pattern that while n is increasing, while n is increasing, how the output like what is the nature of output, right? We just need to think about this in that way. We need to think about nature of output, and we will certainly be able to realize what the problem is all about. This I'm just giving you a hint. This problem is very basic problem that every one of us encounters while learning a language. So this is not a this is not certainly something out of the box. While n is 1, we can have one step. While n is 2, we can have while n is 2 we can have two steps. While n is 3, we can have three steps. Now while n is 4, let's just think about when the case is of 4. We can first way is that we can have 1 comma 1 comma 1 comma 1. Second way we can have is 2 comma 1. Third way 2 comma 2 comma 2, and third is 1 comma 1 comma 2. Yes, third is 1 comma 1 comma 2, then 1 1 2, right? Fifth one being 1 comma 2 comma 1. I guess these are the amount of distant ways we can go through, like the zeroth stair till nth stair, right? When n is equals to 4. So when n is equals to 4, I've just like added up here, and what we are doing is essentially we are just breaking down 2 into 1 1, and then this 2 into, yeah, it should be 2 comma 1 1, right? We're just essentially breaking down these numbers or adding up these numbers in a particular way, and now we got our answer. Our answer is 5. When n is 4, we are getting the result out, or the output as 5. So if you will go ahead and check for n equals to 4 or n equals to 6, you can do it ahead. You can go ahead and do it. You will find a series like this, a very familiar series. You will find a series like 1 2 3 5 8 13 and so on. Isn't this series a little familiar to us? This series is something which is known as Fibonacci series, right? Fibonacci series. And a Fibonacci series is a series in which a certain nth number is dependent upon n minus 1 and n minus 2. Like it is dependent upon previous two numbers in the series, right? Like this is the relation. So if we try to understand DP through this problem, what I will be telling you is DP is nothing. Okay, so let's talk about DP right now. So DP is nothing but recursion with optimization. Recursion is nothing but like DP is nothing but recursion with optimization. Recursion means we are exploring all paths, exploring everything. We will be essentially breaking down a bigger chunk of problem into smaller sub problems, and then we will be solving it ahead. This is what recursion is essentially, right? And we will keep dividing the sub problem until we reach a base case. A base case is something which will be same in every path. Every path will end up with a base case. Every other path will end up with a base case, and then the result will go on ahead and ahead until we reach the original problem. And by stacking up the solution one by one, we will stack solution of base case plus stack solution of base case plus one solution, like let's say, and solution of base case plus n minus 1. Yes, and when we add everything we will get the original solution of this problem. So I will not be going into much depth, but we all know like Fibonacci series. I'm just considering we all have basic knowledge about like for loops, if else statement about C++. Okay, so the thing here is that the thing here is that we essentially use for loops in order to find Fibonacci series. As I've already given you the relation, which is that an nth number of Fibonacci series is 1, 2, 3, 5, 8, 13, yes, and so on. Every number is dependent upon two numbers. Every number is dependent upon two numbers. See, 3 plus 5 is 8, 13 is equals to 5 plus 8 equals 13, and so on. If you will try to do it by yourself, it is very good. So, uh, this problem, like climbing stairs, is essentially like if you understand the pattern, you will look that this is nothing but Fibonacci series, and Fibonacci series is nothing that like out of the world. We all know about Fibonacci series, right? So let's try to understand DP through it. So now DP is of two types. Like this, okay. So DP is of two types. Something known as memoization. Let's call memo in short, and the second thing is tabulation. Okay, tabulation. These are the two different types of DP. What it is essentially about, when we talk about memoization is nothing but when we are like this function is broken down into this function has been broken down into this function. Let's do it like this. Okay, so a function is broken down into smaller functions, into smaller functions. So this until they reach a base case and something like that. So we essentially see a tree here in this recursion. So this is a recursion tree. This is a recursion tree. And what memoization? Memoization and tabulation are both forms of optimization. Optimization of recursion. Uh, so we are just optimizing our recursion through these two techniques. Let's say first technique is known as memoization. Memoization is what? Memoization is like storing elements into like it is essentially storing elements, storing solution of these subproblems. Like I've broken down this and okay, so how will like let's do the problem and we will understand along the way what I'm talking about. What I'm talking about, we will understand along the way. So let's try to do this problem and I will eventually tell you about everything. We will be unraveling things. It is like a gift, right? We're unraveling slowly, in a tender way, but we will soon reach to an end. Okay, so it's like climbing stairs. We're given m, and n will be till 45. I guess any solution will work. Optimization. Okay, I will not. First of all, let us not optimize the solution. We will just do it in a very simple way, in a very simple fashion. So, and we will do it in a recursion format. First, we will take a base case. If n is exactly equals to 1, return something. If n is exactly equals to 0, return something. So what happens when like it starts from when it is 0 it's 0, when it's 1 it's, so how does the sequence starts when it's like 1 comma 1 then 2, right? So if it is 0 we will return 1, if it is 1 we will return like we will return n, and then what we will be doing is return prime stairs of n minus 1 plus minus 2. Oh, yes. So like this is a very basic thing. Now let me tell you how it is working. The way it is working is you just need to visualize it. We just need to visualize it, right? If there is, let's say, so we just need to visualize it. Let's say n is given to us as 6. Okay, so now we will have two function calls because this particular solution is dependent upon n minus 1 and n minus 2, summation of these two things, right? So we will take function of n minus 1 which is 5 and function of n minus 2 which is 4, right? Now we have broken down this bigger problem into smaller sub problem, and then f of 5 will be solved using f of 4 and f of 3, and f of 4 will be solved using f of 3 and f of 2, right? Then say f of 4, let me just fill this table, recursion tree, function of 2, function of 1, function of 1, function of 0, function of 2, function of 1, function of 1, function of 0. So let us not, like, it will be a disaster if we will have a difficulty in understanding if I draw the whole tree, right? So just for our simplicity, let's go through every other base case within this tree. Like this is the base case, right? And this is the base case. Yes, so these are all the base cases which we will hit, and then the solution will go upwards. Like if f of 0 is there, we will return 1, and if f of 1 is there, we will return 1. So now f of 2, solution for f of 2 is 2, right? And if we will take this, now we got the solution of f of 2 is as 2, we will return 2 from here and we will return 1 from here. So essentially f of 3 will be 3, and now f of 3 plus f of 2 is what? 5, right? And then this 5 will go ahead, like this result will come up here, it will be added with the left subtree. So answer of the right subtree plus answer of the left subtree, this is the solution. Now one thing to understand about this problem is, like, do we want redundancy in our code? A certain sub problem is being solved multiple times. You can observe here f of 2 is being solved here, f of 2 is being solved here, And same thing, like f of 3 is here, f of 4 is been solved, like f of 4 we are solving it multiple times. So what I'm telling you is that we are solving the same problem again and again and again. So this is recursion, but the problem with recursion is that it will increase the time complexity. This whole thing will increase the time complexity. And like the time complexity here will be like big O of n raised to power something. Okay, okay, so wait a minute. So what I'm trying to tell you is that it will be big O of this height of the tree, n raised to power height of the tree, like n log n. Yes, log n will big of log n will be the time complexity. And if we can decrease this time complexity by doing what, we can essentially save all the solution of these problems. If we got this f of 4, we can save f of 4 in a array somewhere with like 4 index. We can have the solution is 5, and f of 3 we can store f of 3 solutions 3, so we can store f of 3 as this, right? And if we will get 0 1 2, so we can store all the solution into a place in an array. And after storing all of these solutions, we can like, if we will first of all, like if f of 4 is being solved, the the way how things go in recursion is that we first go through the left subtree. So while going through the left subtree, we have calculated f of 5, we have calculated f of 4, we have calculated f of 3. And soon as we have calculated f of 4, we will be updating the value of f of 4 in a dp vector. And then when we will go to the right subtree, we already have the value of f of 4, so we don't really need to solve this much big part of the subtree. So what we will essentially do is we will save the result somewhere, so that our time complexity will be like big of n. Our time complexity will be improved in a very good way. So let's try to do this and see. I'm not gonna submit this code right now. uh, let's just go with the memo. Yes, and this technique which I'm using here is known as memoization. This technique which I'm using right now is known as memoization. It's like we are memorizing the solutions in a place, and then we are using it whenever required, right? So you can understand it through that point, like in that manner. Okay, so let's try to implement memoization. So for memoization, I obviously need something, another function, because I will need to have a vector, right, which will store the result. So return recursion. Recursion will have int n, and it will have recursion will have int n, and it will have a vector known as dp, right? So all I need to do is initialize this dp. Okay, we will initialize till n, right, 1. Yes, let's take just one extra, and -1 means that a part. So what we will do is we will take we will take a vector. We will take a vector in which we will store solutions of a function of 0, function of 1, function of 2, function of 3, function of 4, function of 5, function of 6, function of, like, still 6 we are doing here till now. So it will store values. So we will first initialize it with minus 1 minus 1 minus 1 minus 1 minus 1 minus 1, and as soon as we will get the result of f of 4, we will update our value in f of 4, which was like f of 0 is 1, f of 1 is 1. Then f of 2 will update the value of f of 2 to 2. Then we will update value of f of 3 to 3. Then we will update value of f of 5 to 5, right? So this is how we will be updating our values. And if a certain value is minus 1, that means its value has not been updated. This sub problem has not been solved. This sub problem has not been solved. So let's do it. We'll have the base case as we had it. uh, it will be, let's say, and okay, so we'll be using memoization here. If okay, I guess we are good to go. There is a problem in our code. RECURSIN. Okay, so we are not having the second parameter in place. Yes, I can go and submit the solution. So yes, wait, we are not. What we are not doing is we are not updating DP. I've not written the code where we update DP, so it is really important. DP of n is equals to. Now we can submit this code. So yes, now the solution has been accepted. So the only problem in our code was that yes, I was using DP, but I was using a vector named DP, but I was not updating it. So at this point, this line return dpn, what it does, it simultaneously do two things. First of all, it will update a value at f of n, and then it will call and return like this function which we are solving right now. And the second thing to understand here is this vector. See this vector int address of dp. Whenever we are calling a vector inside a function, we should always add this symbol and, because if you are not adding the symbol, it will have multiple copies generated throughout. It will have the, the amount of copies that will be generated is this humongous amount of copies that it will generate. So the space complexity will be disastrous, right? So this is how we use it. And there is this is memoization. Let me remind you, this is memoization. Memoization is a technique in db in which we store elements in a vector, like store solution in a vector, and we use it afterwards when we feel like we can find answer of a sub problem, and that we encounter that problem later on in the recursion tree. We directly have an answer and we pick that answer from this point and dump it into the place. Okay, so now let's go through a different way of, like, a different method of dp. So we have explored memoization. What other thing is left? So the thing left is tabulation. So as you can see, tabulation. Before understanding tabulation, let's talk about memoization a little bit. So what it does is it creates sub problems. Like, it is essentially recursion. If we people know about it, right? Function. What memoization does is, memoization just finds the solution, like which I have already told you. It is Memoization is a top to down approach, right? Can we have another approach, such as we start from the base case? We already start from the base case because we already have values of a base case. We have values within the base case, right? So can we do something like this? We will, like, then we are going upwards to the nth problem. So this is what I'm talking about is nothing but tabulation. Tabulation is a down to top approach, and memoization is top to down approach. So this is the difference between memoization and tabulation. This is the difference. So in tabulation, what we do is we have this vector and 0. We have, let's take another pen. So we have 0 and we have 1 as our base cases. Both contain value of 1. Then we can use these two values to find function of 2, which is 2. Then 3 is to be calculated by summation of 1 and 2. Function of summation, like function of 1 and 2, it will be 3, and so on. So we will just have these two things and we will add up. It is the basic case which we do with for loop for Fibonacci series, right? Let us start with vectors. Int plus 1 plus 2 We don't even need this -1, but we can have dp of 0 as 1, dp of 1 as dp of 1 as 1. We can start a for loop. We need to start for loop from I equals to 2, I smaller than n, I plus plus, dp of I will be equals to dp of I minus 1 plus dp of I minus 2. And yes, then we'll go ahead, we'll go till n or equal to, right? And then what we will do is return dp of n. Okay, so this solution will work if, like, this solution is perfect when the value of n is from 2, right? Like, we at least have n's value till 2, but since n can be from 1, since n can be from 1, we can obviously, we will have to write a base case, or like, not a base case, it will be okay. So if n is exactly equals to 1, we will return n. This might, we can say this is to the video. Let me just do it. Yeah, this solution is also accepted, and there is one more method of implementing this tabulation. It is through previous. We can like, what we are having here right now. The time complexity of our code is big of n, and space complexity is big of n when we take dp, right? We can even reduce the space complexity to, like, just few variables, previous and previous to and current. We can have like a pointers strategy. We can remove this by altering this code. We can even reduce the space complexity. So we can remove this vector. We can take it as pre 2, pre 1, right? And current equals to pre 2, pre 1 plus pre 2, and every time we can update, the pointers. Pre 1 will have the value of current, pre 2 will have the value of pre 1, and current will be reinitialized every time. Yes, and then we, at last, we can just return pre 1. Okay, so I have not declared these variables, which I need to do. Hmm, to output. So our code is wrong somewhere. Let's see if I can find where the problem lies. 3 when so the thing is that first of all I'm updating previous of 1, and then I'm updating previous of 2, and previous of 2 carries which value? Previous of 2 carries previous of 1 value, right? So this is something wrong. I should write this condition after this condition. I should write it below. Now it should run. Okay, so let's submit this problem. Yes, so we are done, and let's summarize everything that we have done in this lecture. First thing, we discussed about what really DP is, and then we understood about memoization, and then we understood about tabulation. Okay, and then we discussed two ways of tabulation in this climbing stairs problem. We we understood everything through solving lead code problem number 70. So let's see you guys again in another video. I hope you liked this video, and if you liked this video, I would just tell you to like I would tell you to like and subscribe to my channel, where I will be posting such content daily.